Okay, so to wrap up our videos on word problems for now, we'll get to them later. We're going to talk about mixture problems. Mixture problems give students fits a lot of times. They don't know how to work with them. And so I'd like to spend some time on this video really explaining them about how to be successful at solving mixture problems. Because if you are in beginning algebra, which is probably why you're taking the video, you are going to have to do mixture problems. And you can either just say, skip it, and miss some points on your test. I guess that's possible. Or you can understand them and get those points on your test and actually be good at them. Are they relevant? Yeah, they really are. A lot of times, maybe not beginning nurses, but nurses and pharmacists actually have to do this stuff. Yeah, they have computer programs, but they also need to know how those things work to be able to at least see if they made a mistake in the computer. That happens a lot. You do not want to be the person who gives someone a wrong dosage. That's negligence, and that means you're going to get a lawsuit. That sucks. So anyhow, mixture problems really are relevant, and you're gonna see that in some of these things. So I actually did this one in my own vehicle. I have all old cars and they all leak stuff. So in my car, I want somewhere between about a 40 and a 50% antifreeze solution. So I had some 70%, I had some 30% because I've been watering it down, which you're not supposed to do, and I needed 45%. So we're going to work through this mixture problem and one that's different. So I'm going to show you both ways that these things work. If you have not watched the distance equals rate times time video, the one right before this, I really encourage you, if you're like, I just want to skip it, I really encourage you to watch that before this video because a lot of the same techniques are used to set these problems up. Similar table, same technique on one of these problems. So if you haven't watched it, watch it, or watch this first and then go right back and watch it because either way it'll solidify the ideas I'm trying to get you to do. So let's read through the mixture problem. It is a word problem after all. We got to read through it. You need a 45% solution of antifreeze. How much 70% antifreeze do you have to mix with 10 gallons of 30% antifreeze to create the solution? Well, hopefully that makes sense that this is possible even. So you have 70, you have 30, you can get pretty much any mixture between 70 and 30 by diluting the 70% to get down to 45% in this case. Now, just like distance equals rate times time, a table really helps us. This isn't so much a formula. We'll talk about the formula. The formula comes from percents. The formula is the idea that to find a percentage of a number, you just have to multiply. We're going to be doing that. So that's part of the formula. This is going to be also our verbal model. This graphic organizer helps us set up kind of the picture/verbal model of this word problem. So here's how to set up a mixture problem and get it right every time. Put what you have in the first two rows. Put what you need in the bottom row. In distance equals rate times time, it was what you did and total. Kind of a similar idea here. We're going to be using that totaling idea. Put what you have here and what you need here. On the two columns going down, put the amount, so like gallons, milliliters, the amount that you're mixing, so that would be the volume idea, and the solution. How much of that volume is actually solution, actually antifreeze, actually acid, actually drug, or whatever that happens to be, okay? So what you have, what you need, the amount, and the solution, or the mix. Let's see what we have. When I was doing this, I needed 45%. I had 70 and I had 30. So the 45, what I need is going to go down here. I'm going to put 45% down here, what I need. What I have is 70% and 30%. It does not matter what order you put the halves, but the need has to go here. So I had 70%, I had 30%, I needed 45%. If that makes sense, that's awesome. Let's move on. On our columns again, you're going to put the amount. In this case, we're talking gallons. So you can put gallons or you can just put amount. I'm going to do both. Our amount needs to be in gallons. So let's see how much we actually have. Well, let's see, how much did I have? How much 70%? I don't even know. Wait, I don't even know. Variable, that sucker. If you don't know an amount, it is going to be a variable. So I'm gonna hang on for just a second on that. So how much 70%? I don't know. Do you need to mix with 10 gallons of 30%? If this sounds familiar, this is exactly what we did in distance equals rate times time. We fill out what we know. We read the problem carefully. We fill out what we know. I know what we have, I know what we need, and I know that I have 10 gallons of this. Interestingly, that's all we need to know. The rest of it we can actually figure out. So, I know I've got 10 gallons of 30%. How many gallons of 70% do I need to mix with that? I don't know. Let's call it X. Here's the big deal. Here's what I gotta have you get, what I have to have you understand. However many gallons of this you mix with however many gallons of this must equal however many gallons of this. In other words, if you're mixing 5 gallons with 10 gallons, you're going to get 15 gallons. If you're mixing 20 gallons with 10 gallons, you're going to get 30 gallons. If you're mixing I don't know how many gallons with 10 gallons, you're going to add them. These have to add up. So what you have has to add up to what you need. If you have 10 gallons here and I don't know, X gallons here, then your total amount of what you're going to have at the very end, what you need, is going to be X plus 10. Let this soak in for a little bit. When you're mixing stuff together, you get 10 gallons in a vat. You're going to pour in gallons until that equals 45%. However much you pour in is going to be added to the 10 gallons. This has to add up. I don't know how much plus 10 gallons equals X plus 10. Let's do a little recap to make sure you're getting this, okay? What you have goes here, what you need goes here, the amount goes here. Fill in what you know. You're not going to know any of this over here right now. You're not going to know this column yet. We figured that out in just a second with a formula, and you already know the formula. So we have 10 gallons of 30. We have, I don't know how much it's going to take, but I do know that these two have to add up. That's it. That's all you got to know for right now. Next, we use the idea of pure solution. Pure solution has to add up. How much solution this gives you plus how much solution this gives you have to add up to how much solution you get in total, like pure acid, pure drug, pure solution there. How to find this? It's not as hard as you might think. Percents are very nice creatures. To find a percent of something, you just have to multiply it. To find 50% of body weight, you multiply the body weight by 0.5, you get half of it. To find 70% of an amount of fluid, you multiply 70%, if that's 70% antifreeze, 70% times however many gallons we have, is going to give you the amount of actual, whole, undiluted, pure antifreeze in them. If you have 10 gallons and only 30% of it's antifreeze, so it's all mixed up, it's diluted, to find the percent of any value, just multiply them. So if we have 30% antifreeze and there's 10 gallons of it, there's actually 30% times 10 gallons of actual undiluted 100% pure antifreeze. So in other words, once you found this, just multiply straight across. That's how you find your solution. In this case, our solution is pure antifreeze. Pure antifreeze. Anytime you want to find a percent of any number ever, you just multiply it. So take 70% times X, take 30% times 10, and take 45% times X plus 10. Now you're going to notice something I do different than a lot of other teachers and probably textbooks. I don't put a decimal here. Even though that's 70%, it should be 0.7, right? You should have 0.7 times X. You should have 0.3 times 10. You should have 0.45 times X plus 10. But here's the deal. When you get your equation, and I'll show you this in a minute if you want, when you get your equation, you'd immediately be moving decimals anyway. So it's not even relevant to write them. Don't even worry about it, okay? Unless your teacher's a real stickler and they make you write the little decimal. I'm not, but you might not have me. Check this out. So the whole thing one more time. Once you have what you need, the amounts, you're usually given an amount. If you're not, I can teach you how to do that in the next example. You're usually not given at least one amount. That becomes your variable. This, no matter what, it has to add up. This plus this has to equal that, no matter what. Keep that in mind. To find any percent of any solution or any other number, multiply your percent times the amount you have. Multiply your percent times the amount you have. Multiply the percent times the amount that you need. That's going to give you the pure solution, a pure undiluted antifreeze in this case. Now, here's the deal. Just like your amounts have to add up, the actual proportion of pure solution has to add up. The amount of pure antifreeze here plus the amount of pure antifreeze here has to equal the amount of pure antifreeze here. Add them. Just add them. Now, I mentioned a little blurb like 30 seconds ago. Why I don't do that. Why I don't have the decimal. Can you see it? Can you think back to equations, linear equations that involved fractions and decimals? As soon as we have a decimal in an equation, you're multiplying both sides by, in this case, 100. The first thing you're doing would be moving your decimal, and moving your decimal on every single one of those terms. That's one big fat term, that's one big fat term, and that's one big fat term right now. You'd move the decimal on the 30, the 70, the 45, which means right here, you can put it, but you don't have to put it. Not putting that decimal immediately changes, multiplies both sides of your equation by 100. You still get the same answer, don't even worry about it. And now we have something that's not horrible to figure out. We know that we have 70x plus 300. If we do a little bit of distribution, we now have something that's really similar. Sure, big numbers, but similar to what we've seen before. We've got an equation. We have 4 terms, 2 on each side. There's no like terms, none at all, but we do have a smaller variable. Let's get rid of that smaller variable. You know, you really should be trying this on your own, seeing if you can still solve linear equations. Right now, our variable side drives the problem. Get rid of your constant. And your last step, divide. We get 6. Now, what's that mean? Interpret it. Don't just leave your teacher hanging. Don't just leave the word problem hanging. This asks you for a certain question. If I have 10 gallons of 30% antifreeze and I have this jug of 70% that I saved, I'm going to have to mix how much in there to get 45%? Well, that's why we write this stuff out. Because now we go, well, x is 6. What's that mean? Well, go back here. X is 6 says that I need 6 gallons of 70% antifreeze to mix into 10 gallons of 30. So I have a jug or a container of 10 gallons of 30%. All I've got to do is pour in 6 gallons of 70%, and I know for sure that's a 45% solution. In fact, I would have 6, 10, oh hey, 6 plus 10. I'd have 16 gallons of 45% solution. That's how you work a mixture problem. Now, we're going to do one more. Because the setup's different, this will cover the 2 types of mixture problems that you're going to be exposed to. So let's do this last one, and then we'll be done with all of our word problems for a little while. These are worded so funny, and I get it. It's just the way they are. How much 10% solution needs to be mixed with how much 30% solution, and how much? That's crazy. That looks like 2 variables. But you can't. You can't yet. Now, this is crazy, but later on when we deal with systems, we will revisit these problems, and I will show you how to do this with 2 different variables, with systems of equations. Anyway, how much 10% needs to be mixed with how much 30% to create 20 milliliters of 25%? Why don't you try to fill out this table right now? Don't wait for me. That's really bad way to learn. Try to fill it out now. Even if you're wrong, who cares? What, you waste like 10 seconds? Put what you have here. Put what you need here, put the amount, it would be milliliters here, and put solution or pure solution here. Try that right now. I'm going to start filling out, of course, as we go, but what we have, how much 10% needs to be mixed with how much 30% to get 25%. The 25% is how much we need. How much we have, apparently, is 10% and 30% solution. So how much we have is, or what we have is how much they're asking us to mix. So we're kind of assuming we have that because we need this stuff to get our 25%. Our amount, in this case is milliliters. To create, to create a 25%, to create 20 milliliters of 25%. So look at that. Do we know how much 10% we have? Actually, that's in the question. How much 10%? Do we know how much 30% we have? That's also in the question. How much 30%? Do we know how much we need? Yes, 20 milliliters. This is a more realistic version. Okay, this assumes that you're not going to cut your 30% at all, that you're going to get an unknown amount of 45%. This is more realistic. You don't want to waste this stuff. So this is usually how mixture problems work most of the time. They say, well, we want to end with a certain amount of a certain percent. This would be like the drug example. If you're mixing like pharmaceuticals or whatever, you don't want to mix over, you don't want to mix under. You want to end with a certain amount of a certain mixture. That's how this would work. So we don't know this. We don't know this. We want this. We want 20 milliliters here. Do you see the difference in these problems already? Do you see how this one, you're given an amount that you have already. Here, you're given an amount that you need already. Now, the way that we fill in the rest of the table, this one I think is easier because you have an amount already. You don't know an amount. They have to add up. This one is very, very similar to the distance equals rate times time video that I had you do last time. That's why I wanted you to watch it first. Because here's the deal. Just like these amounts have to add up, they have to add up. The amount you mix here with this has to add to this. The amount that you mix here with this also has to add to that. The problem is we don't know where to start, and this is where students get really tripped up, just like in distance equals rate times time. Call one of these a variable. You don't know it, obviously, so call it a variable, call it x. And if you see the similarity, I'll be proud of you, okay? The similarity to the last video is, hey, if you know you have to add to 20, and you're calling this one x, this one has to be, think about it, try it on your own if you don't know it. You need these two to add to 20. You need x plus blank space to add to 20. Can you solve for the blank space? Logically, I hope it makes sense that if this plus this equals this, then this equals 20 minus x. If these two have to add to this, then this has to be total minus the part that's added to it. And you can show your work actually. That's got to be 20 minus x. If these two pieces must add to 20, then this blank space has to be 20 minus what you're using up for the 10. Realistic because you're actually adding to a given amount. That's most of the time how mixture problems work. So, does it actually work? Can you add them? Is x plus 20 minus x equal to 20? Yeah, sure. X plus 20 minus x minus x is 0. 20 equals 20. You're good to go. Now, do exactly the same thing for your solution, the pure solution in this case. Again, you can use the decimal or you can just use the percent. It doesn't matter. You'll be changing it anyway. So your little recap here is what you have is 10% and 30%. What you need is 25%. In this case, it's giving you the total amount that you need. The amounts that you have must add to it. They have to add to it. So if you don't know, and whatever one you call x, it doesn't matter. It does not matter. It's just your variable will represent 30 or 10, depending on how you set this up. It doesn't matter. But whatever you call x, the other one is total minus x. That's how that works. Whatever one you call x, the other one is total minus x, because these must add to that. Now, your solution works the same way. To find the percentage of any value, just multiply. So this would be 10x, 30 times 20 minus x, no problem. And then 25 times 20. And the same logic holds. If this is the amount of pure solution and this is the amount of pure solution, the amount that you have is going to add up to the amount that you need. The amount of pure solution here plus the amount of pure solution here equals the amount of total pure solution that you have. Just add these up. It's going to look extremely similar to this. We'll go through it to make sure you get the right answer, but the idea is exactly the same. So doing a little work, that they're linear equations. This is why we practice distribution. Practicing that stuff that doesn't look real, like distribution, eventually becomes real for word problems. That's why we practice the easy stuff. Like, distribution wasn't easy. Yeah, no, but it's getting us to something even harder. So practicing this stuff makes it so that when you actually fill out your mixture problem, you don't get tripped up with the little things like distribution and combine like terms. Let's see, what is that? Can't even do that in my head right now. Yeah, 500. So if we combine some like terms, notice something. No like terms here, but yes like terms here. You only have one variable since you combine your like terms on the left-hand side. Let's get rid of the constant. By the way, when I referenced the formula, this was the formula I was talking about. The percent times the value equals the actual pure, undiluted solution in that. When we divide by negative 20, we get positive 5. Go ahead and interpret that. Write a full sentence. What this says is that we need, oh wow, it's asked for two different solutions, doesn't it? So we need to answer both of these. How much 10% do you need? How much 30% do you need? This is where your table comes in really handy, because depending on what you called x, that would answer your question. So if you called x 10%, you get 5. If you called x 30%, x would have been 15. They would add to 20. So it kind of depends on what you call x, depending on what your correct answer is. The correct answer overall, when you answer this question on both of the things they referenced, was you need 5 milliliters, since x was 5, x fit in this box, you need 5 milliliters of 10% mixed with 15 milliliters of 30%, and that will give you 20 milliliters of 25%. That is how mixture problems work. You need to try these. Before you go any further, please try them. Go through both examples without the notes if you can. Use the notes a couple times if you have to, but by the time you get to your homework, I don't want this to be frustrating. I don't want it to be like, oh, I'm pulling my hair out because I really don't get it. That's really frustrating. So work your way through this. Get the concept of how to find these two and you'll be good to go. How to find these two and you'll be good to go. Give that a try, and then we're done with word problems for a while. Yay.